The video is being recorded now. Okay, so let's start. So good afternoon, everyone. This is lecture 15 of IC242 Continuum Mechanics. We've been talking about stress tensor. Just a quick recap of the last lecture. So we talked about the force and moment equilibrium equations. So in the last lecture, in terms of force equilibrium, we discussed this equation called the local equilibrium equation. So which is the equation that relates the divergence of the stress tensor and the body force vector Bi. Okay, the other equation we discussed was the moment equilibrium. So I'll quickly go back to the last week's lecture notes and do a quick recap, but I'm just discussing the agenda right now. So then we did the moment equilibrium along with the force equilibrium, which finally resulted in the relation that sigma is symmetric. That is sigma ij is equal to sigma ji. That's a very important relation, and we should remember what is which equilibrium equation results in the symmetry of stress tensor. Now, in this moment equilibrium, we assume that there are no concentrated moments at a given point P. Now, this is not always true, this is true for most of the cases. So 99.99% cases, we'll have situations where there is no concentrated moment. So that means that sigma ij is equal to sigma ji. But in case it is not true, that is, if we have a material where there is some concentrated moment at a given point P, then we will not have the symmetry of stress tensor in that case. And these materials are called polar materials. So for polar materials, the stress tensor is not symmetric, but the situations that we deal with in this course, the stress tensor will be symmetric. That is, there will be no concentrated moment at a given point P, in any given point P in the domain. Okay. So if we have the case that sigma ij is equal to sigma ji, which is true for most of the cases, including what we'll discuss, so we can replace sigma sigma ji with sigma ij, and our equilibrium equation becomes sigma ij comma j instead of sigma ji comma j, because sigma is symmetric. Okay, so this is, if you see this form of the equation, this is also true, but it takes into account the moment equilibrium, that is the symmetry of stress tensor. Okay, so let's quickly go back to last week's lecture notes and do a quick recap. So what we started with was that we took a body, the body with a total volume of omega, and we said that the whole body or any subset or any subpart of the body, it's under force and moment equilibrium. So if we apply the force equilibrium equation on the whole body to start with, using the Gauss divergence theorem, we finally get this form of the equation, which is the integral of sigma ji comma j plus rho bi over the whole domain is 0. Now, the choice of the domain for applying the force equilibrium was quite arbitrary, because as we said, the body is at equilibrium. That means the net force acting on any subpart of the body is 0, because if any subpart has a non-zero force acting on it, then that subpart will start accelerating from Newton's second law of motion. Force equals mass times acceleration. So for any subpart of the body to be in equilibrium, that is no acceleration, then the net force acting on any subpart of the body also has to be 0. So that means our choice of omega for the force equilibrium is arbitrary. So that means the term under the integral has to be identically 0, which results in the local equilibrium equation. The reason we use the word local is because it is valid at each and every point in the domain. Because if you think about it, this Bi, the body force, and sigma, they are defined at some point. We took an arbitrary point P. So it's local in the sense of its applicability to each and every point inside the domain. So you can apply this equation at every point inside the domain. So this was the force equilibrium equation. The next, we discussed the moment equilibrium. So we said that the net moment or the net torque of the body forces, that is these ones, rho bi's, and the surface forces acting on the surface of the domain that we have taken, the net torque or the net moment of these forces at any given point, the one we choose for the origin for convenience. So this net moment has to be zero because we are considering a non-polar material, that is materials which do not have any concentrated moment at points. So when we do this, when we apply a bit of a tensor calculus, finally we get the relation that epsilon ijk sigma ij equals 0. And then we discussed what this actually expands to. So for the three different cases, because this equation is a vector equation, you can see that the number of free indices in this equation is only 1, k. That means it's a vector equation. So a vector being equal to 0 means all its three components are 0. So we applied it for the three components, k equals 1, k equals 2, and k equals 3. So when we apply this equilibrium on the three components, sorry, when we apply the equality of this vector being 0 for the three components, what we get is the symmetry of sigma. That is, we get the relation that sigma is symmetric. Okay. Again, as I said, that it's a very important relation. So please remember that it's the moment equilibrium equations that lead to the symmetry of stress tensor. Okay, so this completes the recap from the last lecture. And then if we don't have any questions, we'll move on to this present lecture for today. Any questions? None? All right. I'm just assuming that you can hear me properly. If there's any problem with hearing this lecture, please let me know. All right. So let's do an example. So let me look for a problem from the book and see if we can apply this equilibrium equation to something real. So let's try problem 3.7. So let's only do the first part. So the problem says that you have a stress tensor sigma, which is given in terms of the position vector coordinates in this way. So you have the three rows here. So what this means is that it's a stress field, because the body has different points. So what it says is that the stress field is given as this. So depending on at which point, depending on what the x1, x2, and x3 values are, which are the three components of the position vector, the stress tensor is given using this relation. Okay. So you have to find now it's already given to you that the body is under equilibrium. That is, the equilibrium equations are to be satisfied everywhere. That means the body is under equilibrium. So given the body is under equilibrium, you have to show, oh sorry, you have to find the body force components. Now equilibrium, as we discussed, means force equilibrium as well as moment equilibrium. Now if I ask you, is the moment equilibrium applied here? So remember, what the moment equilibrium said was that the stress tensor is symmetric. Now if I quickly have a look at my stress tensor here, I can see that it is symmetric. Okay. So that means that since the tensor is symmetric, so moment equilibrium already is applied. So what we have to use is the force equilibrium. So in that case, we can find the value of the body force components. So I'll give you half a minute. So see what approach you have to use. So go back to the local equilibrium equations, because they are valid everywhere in the domain. So see if you can expand those equations and try to find out the value of the body force components. Now the body force is a vector. That is, you have to find the B vector, which has three components, B1, B2, and B3. And you have to find the body force vector field. That is, you have to find this at each and every point in the domain. That is, B1, B2, and B3 are all functions of position vector. Okay, any suggestions? Okay, just a quick request. So Avinash, can you please switch off your video? I mean, I don't mind you having on the video. It's just that if you are on the video, then you'll get recorded into the main video that we record for YouTube. Thank you. Right. So we have a couple of suggestions. So they are that we have to start with the force equilibrium equation. That is right. And we have to differentiate. That is also correct. Because if we write our force equilibrium equation, then the equation says sigma ij comma j plus rho bi equals 0. Now, if I closely look at this equation, we actually have three equations here because we have one free index, which is I. That means I can put I equal to 1, that gives me the first equation or the x direction equation, I equal to 2 and I equal to 3. So I should be able to write three equations and then expand them and get the value of the three BIs. So let's do that. Okay, so we have to apply the Einstein notation because we have J as the dummy index here. So when we do that for I equal to 1, we have this one equation. Now the first one is sigma 1, 1, comma 1. Now if we look at this sigma that's been given to us, sigma 1, 1 is x1, x2. Okay, so we substitute that here. So sigma 1, 1, comma 1 is nothing but del sigma 1, 1 upon del x1. So if sigma 1, 1 is x1, x2 as given here. So del of sigma x1, x2 by del x1 is nothing but x2. It's a partial derivative. Similarly, sigma 1, 2, comma 2. Now sigma 1, 2 is nothing but x2 square. You would want to take the partial derivative of this with respect to x2. So this becomes twice of x2. And then sigma 1, 3, comma 3. So sigma 1, 3 was nothing but 0. The third term here is 0. So that means the third term here is 0 plus rho b1 equals 0. So from here I can write my b1 as minus 3x2 by rho. Okay. So what we saw was that putting I equal to 1 here, we get the first equation or the equation for the first component of B. And you can see that it's a field, as in this component changes if I change my position vector. It depends on x2 only, but it would have depended on x1, x2, and x3, all three of them. So it's the body force field, the first component of the body force field vector. If I apply the same idea for I equal to 2, I won't do it here. That gives you B2. And if I apply this equation for I equal to 3, then I get the B3 vector, B3 component, sorry. So once you have all three components, you have the vector P. Any questions on that? Okay, if there's no question, then we'll move on. The next topic that we discuss in this course is on stress transformation. Now, we already have discussed the transformation laws for nth order tensors. So, using that particularly for stress tensor, which is a second order tensor, should not be difficult. So, you already know the mathematics. So, what we'll do in today's lecture is we'll try to apply that to a given stress to a given stress value and see if we can apply those ideas using numerical values given to us. So let's try to read this problem. The problem is an example of the book 351. The problem says that the stress tensor sigma is given to us at a given point P. So it's been given to us at a given point P. In fact, if I draw the coordinate system, it's been given to us in this Cartesian coordinate system, which is P x1, x2, x3. Now remember that stress tensor is nothing but the stress vector or the traction vector at three mutually perpendicular planes. So unless I define a coordinate system, it does not make any sense to define a sigma. Okay, the sigma is dependent, the components of sigma are dependent on the coordinate system we choose because they are nothing but the stress vector components in three mutually perpendicular planes in the E1, E2 and E3 directions. So this sigma with the 9 components given to us here above is given to us for this blue coordinate system that I've just drawn. Okay, so this is the non-primed coordinate system. Now, it's been told to us that we have a prime coordinate axis, which is obtained by taking a 45-degree counterclockwise rotation about the x3 axis. So what we do is we keep the x3 axis fixed. And we rotate the current or the blue coordinate system 45 degrees counterclockwise. Okay. So we rotate the coordinate system 45 degrees counterclockwise, and we obtain this red coordinate system, which is the prime coordinate system. So we have x1 prime, x2 prime, and x3 prime is the same as x3. So our job, the problem given to us is to find sigma ij prime. That is, we have to find the 9 components of sigma in the red or the prime coordinate system. Now, if you go back, we do a quick recap. We learned that sigma ij prime is nothing but AIP, AJQ, and sigma PQ. Okay, so that was the stress transformation rule, or in fact, I should write the tensor transformation rule. We can also write this in the symbolic notation. Which is sigma prime is A sigma A transpose. Okay, so whichever notation, whichever form is more comfortable, you can use that. So going back here, to be able to find sigma prime, we have to find the 9 components of the transformation matrix A. Now, if you remember, Aij is the I comma jth component of the transformation matrix. It was given as a dot product between Ei prime and Ej. Okay, so the first index of A is nothing but the primed coordinate, prime unit vector, and the second index, which is J here, is the non-primed unit vector ej. Okay. So using these ideas, we can find our A matrix. So let's try to write that here. It just becomes easier because we already have the coordinate system in front of us. So what's A11? The A11 is a dot product between x1 prime and x1. That is this one and this one. So we can see that direction cosine, or the cos of the angle between these two, is cos 45 degrees, which is 1 by root 2. Okay, in case there's any question, there's any confusion, please feel free to ask questions. Okay. Now the next one is A12, that is the angle between x1 prime and x2. Okay, again, this is again 45 degrees, so we have a cos 45 in this case, or if you are using theta instead of 45, the red 45, then you can use this as sine theta. Okay, so we can make it more general, but for now we'll just write this as cos 45, which is 1 by root 2 again. All right, then the third column in the first row, which is A13, is the angle between E1 prime and E3. So we can see that they are at right angles to each other because the rotation was done about x3. So the x1 x2 plane, or the x1 prime x2 plane, is still perpendicular to x3. So x1 prime is perpendicular to x3. So we get a 0 here. Okay. Now then the next one is A21. That is the angle between x2 prime, sorry, the cos of the angle between x2 prime and x1. Now this, if you see, is nothing but, what's this angle? This is 90 plus 45. Okay. So this becomes minus 1 by root 2. Okay, cos in the second quadrant is negative. Then so next we have A22, that is the angle between the dot product of E2 prime, and E2, so which is cos 45, which is 1 by root 2. Okay, so this is these two. And the third one, which is A23, again is 0. Okay, now going to the third row, so A31, now that's the angle between x3 prime and x1. This we see is 90 degrees, okay, because the rotation was done about x3. That means x3 prime is the same as x3, and x1 and x2 are still perpendicular to this plane. So this becomes a 0 to the first two. And the third one, which is the angle between x3 prime and x3, or the dot product of x3 prime and x3, since they are both in the same direction, then this is a 1. So let me confirm that in the book. Yeah, it's correct. All right, so we've got the A matrix now. So it's quite simple now. So we have to find sigma prime, which is nothing but A matrix, which is 1 by root 2 and the third matrix is A transpose. So I can find my A transpose by transposing the A matrix that we just found out. So I'll leave it to you. You can easily do the multiplication and write the final answer. Units are megapascals. Okay, so if we do a quick check, our sigma that was given to us, which is this one, it was symmetric. You can see that, and our sigma prime, which is the final one, is also symmetric. Okay, so it still satisfies the moment conservation, the moment equilibrium. You will see that sigma prime will always be symmetric. In fact, you can show it for a general case that if sigma is symmetric, then the orthogonal transformation will result in a sigma prime, which is also symmetric. So I leave it to you to show that for a general case. Okay, so let's move on. The next topic in today's lecture is principal stresses and directions. Now again, this has been discussed in the mathematics part. We discussed in a bit of a detail as to what principal values or or the eigenvalues and eigendirections are. Now we call it principal stresses because we'll be talking about the stress tensor in particular as a tensor under consideration. So let's draw and demonstrate that. Okay, so we have a point P and we have a cutting plane in the direction n hat, and we have the stress vector or the traction vector T with superscript n hat because this is the traction vector at point P for the cutting plane in the direction n hat. Now we'll be writing the components of T along n hat and perpendicular to n hat. So if I take a component of T along n hat, then this is called the normal component or sigma n, and the component of T perpendicular to that is called sigma S. Okay, so we'll be using sigma n and sigma s a lot. So sigma n is the normal component of T, that is the component of T along n hat, and sigma s is the shear component of T, that is the component of T which is in the perpendicular plane to n hat. So we can easily say that our T, the normal component of T sigma n is nothing but the dot product between T and n hat. So that's how you find a component of a vector in a given direction. You take a unit vector in that direction and take a dot product of that with the original vector. Similarly, sigma s can be found out by writing the relation that sigma s squared plus sigma n squared is nothing but T dot T, or the square of the T vector magnitude. All right. So getting back to the discussion on principal stresses and directions. Now, in the general discussion, we said that the T vector need not be in the direction of n hat. In fact, we just showed that it has two components, one along n hat and one perpendicular to n hat. But we have some special n hats, or we have some special cutting planes in which our stress vector actually is in the direction of n hat. That is, this is some constant lambda times n hat. Okay, that basically means that sigma s is 0. That is, it has no component in the perpendicular direction. It is completely in the n hat direction only. So that is no shear component. Sigma s equal to 0. Okay, so for these special cutting planes, our stress vector, the traction vector, becomes equal. Sorry, becomes is in the direction of n hat, or the normal plane only. That means it only has a normal component. It has no shear component in the direction of the plane. So we can then write, if you remember that from the Cauchy stress principle, we can write T as sigma dot n, or let's work in the initial notation. That's much better. Okay, we already have shown that. I'm just repeating that. So in the initial notation, I can write my T, the stress vector as sigma ji nj. That's from the Cauchy stress principle. On the right hand side, I can write as lambda times delta ij nj. Okay, so we can apply the substitution property and write this as um, lambda ni. Okay, so we're doing the other way around. So now if I take everything on the left hand side, and I also write, and I also use the symmetry property of sigma. That is, I replace sigma ji in the step above with the sigma ij because sigma is symmetric. So we apply all these together. So we get sigma ij minus lambda delta ij times nj equals 0. Now you know that it has a non-trivial solution. That is, it has a solution for a non-zero n vector if if the matrix sigma minus lambda I is singular. That is, the determinant is 0. Okay, so if you apply this condition, you get a characteristic equation, and which has three solution, or the three lambda values. So that give you the three principal stress values. Okay, so I'll stop here. I'll not go into details of this. You can go back to the discussion on eigenvalues and eigenvectors and discuss that further. Any questions?
Hello. Hello. Hello.
Yes, please. Yeah.
Sir, can we treat that T as a vector, like, because we have seen it is a tensor now? Like here, can we always break it into two components perpendicular?
Right. So T is not a tensor, T is a vector. So there is always a confusion in most cases that T has the same name called stress vector, but it is not a tensor, it is a vector.
Okay.
So you see that when I use the T thing, I have one free index here. Okay, so T is a
Yeah.
vector, and any vector can be written in terms of two components in two mutually perpendicular directions.
So in the previous, what we learned was it was tensor now. Like, what is the difference? Like here, what is the difference from that? Like,
No,
we
no,
have
T
seen that
is
stress is a tensor now. We have seen that thing now.
right. So there's always a confusion that we call it with the same name, but T is not a tensor. T is a vector. So we started with the idea of a stress vector, that is from the Cauchy stress principle. So it's a very important question. So let's quickly go back and check this. All right. So can you see the slide which is on the screen?
Yeah, yeah, I can see. Yeah,
So here we say that we take a very small area, delta gamma star, and we try to find the sum of all the forces which is acting because of the hypothetical part 2 on part 1 of the body. So it's a
yeah,
force. Okay, so we take the sum of all those forces on the very small area delta gamma star, and in the limit that delta gamma star tend to 0, we say
yeah.
that the ratio of this, sorry, let me go back here. So in the limit that delta gamma star tend to 0, the ratio of this delta Fi, which is the sum of the forces acting on delta gamma star, to the area delta gamma star, it has a limit called the stress vector. Okay, so this limit is a vector. It is not a tensor. So
Okay, okay, fine, sir. Okay.
that's the point. So whenever I say T is always a stress vector. Now the confusing part is that the stress thing is also used for a tensor and a vector. So that's the reason the word traction is used. So traction can like remove the confusion of stress being the word stress being used for vector. So whenever there's a
Okay, so
confusion, we can ask you.
when can we treat it as a tensor? Like you have seen that traction is another word, but when we can see that stress as a tensor.
So if you see mathematically, then the T vector can be written as a dot product between sigma and n, where sigma is a tensor.
Okay, okay,
So when we take mathematically the dot product between sigma and n, that gives us a vector, which is the stress vector or the traction vector.
okay, okay, sir.
Okay. So getting back, so there is an example 361. So let's try to do that. So the example says that the sigma value, the stress value at a given point P, so it's at a given point P, it's given to us with respect to an axis P x1, x2, x3. That is, the components of the stress tensor are given with respect to this axis. So we have to determine the principal stresses and the principal directions of sigma at point P. Okay, so it's a solved example from the book. I will not do it, but I'll just write what method you use. So in the last slide, we showed that the when the determinant of sigma ij minus lambda delta ij is 0, that gives us the necessary equations to find the principal values. So you can write that as so all we have to do is we have to expand this determinant and get the three roots of the equation, which are nothing but lambda 1, lambda 2, and lambda 3, or the three principal stresses or the principal values of the stress tensor sigma. It's a very straightforward problem. So I will leave it to you. And the only confusion that people have is on how to find the normal direction or the principal directions of this. So let me show that. So when you solve the characteristic equation, you get your okay, so you get lambda 1 equal to 24. So the three roots are 24, 50, and 75. Sorry, 25. 25, 50, and 75. So let's try to find the first, that is the eigendirection in the first eigenvalue or the first eigendirection. So we'll try to find n1 hat. Now, if you remember, the equation that we wrote was sigma ij. Let's go back to slides. So this equation. Right, so that's our equation. Now we can expand this. So if I write in the matrix form, Okay, so that's the given equation, and you also have a condition that ni is 1. That is, if I expand this becomes so you have a total of 4 equations and you have 3 unknowns, which are the 3 components of the normal vector. So in fact, if you expand A, what you see is that it only has 2 independent equations, and it's not very difficult to see that. So you will get 2 equations from here and 1 equation from here. So using these 3 equations, you can find the 3 normal components n1, n2, and n3. So that's the first normal, and you can do the same exercise for n2 and n3. So that gives you the 3 principal directions or the eigen directions. Right, so there's a question by Manvi that isn't that similar to eigenvalues and eigenvectors? It is similar. It is exactly the same. We are doing the same process. Instead, we call it principal values and principal directions. Exactly the same. So if you're comfortable with that, that's exactly what we're discussing here. Okay. So then I've written a couple of homework questions for you. So let's try to understand what the questions are. The homework problem 1 is, for a symmetric real valued matrix, show that eigenvalues are all real. Now, I stated to you earlier in the mathematics part that if you have a symmetric real valued matrix, which is the sigma here that we're dealing with, all the eigenvalues of the principal values are real. You have to show that mathematically. So a couple of hints are given to you here. So go through these hints and try to show that without looking at the book. The book already discusses the solution, but I want you to try yourself first. It's not very difficult. All right. The second homework problem is you have to show that the principal values. So once you have shown that the principal, once you have shown that the principal values or the eigenvalues are all distinct, are all real, you have to show that the eigen directions or the principal directions are all mutually perpendicular. So there's a mistake here. It's principal directions. You have to show that n1 dot n2 is 0, or to show it in a more general sense, so that's homework problem number 2. And the third homework problem for you is you have to show that the question is, are the principal values of sigma invariant? That is, if I rotate my coordinate system, the new sigma prime I get, and I try to find the eigenvalues of that sigma, are they still the same? So you have to find if the principal values of sigma are invariant, and you have to answer with a reason. You don't have to find the values as such. You just have to show using some mathematical well-known idea that the principal values are invariant or not. Okay, so in the next class, we'll try to solve these problems in the class, but for now I want you to try it yourself. All right, so the last topic, which we'll just quickly introduce, and we won't go into too much detail here. So the topic is about maximum and minimum stress values. So for the case that we've been talking about, that's a given point P and a cutting plane through point P in the n hat direction, which gives us the stress vector t in that direction. So depending on the n hat values, we get different t values. So we talked about the state of stress. So we talked about the state of stress as this infinitely sized array or a tuple, which has the normal directions as the first member of the tuple, and the second member is the corresponding stress vector or the traction vector in that cutting plane at point P. So this is at point P. Now, there are certain directions where the stress values become large. That is, the T values, the magnitude becomes very large. And these n hats or the cutting planes are particularly interesting because they are the ones which can cause issues with fracture or the failure of components. So we have to find these particular n hat values where the stress vector becomes very large or it becomes very small. So what are these? So it's an optimization problem to find the n hat directions for which the t values become large or small. So the way we approach this is we say that sigma n, which we just discussed as the normal component of t, that is the component of t along n hat, and sigma s as a shear component. So we try to find out what the maximum and minimum values of sigma n and sigma s are for any n hat. So the question, the problem here is okay. So there is one particular n hat direction where my sigma n becomes maximum. So you find that n hat and the sigma n max value. Similarly, there's another n hat direction where my sigma n becomes minimum. You find that n hat value and the corresponding sigma n minimum value. So that's number one. Number two is to find, so there is one n hat value where the sigma s value becomes maximum. So you find that n hat value and sigma s max value. Similarly, you find the n hat value and the corresponding sigma s min value. Okay, so that's the problem that we have to solve. And once we do that, we obtain what we wanted. We want those particular n hat directions where things become max or min. Okay. So we will do it mathematically in the next class. So there are two approaches to that. So one is the Lagrange multiplier, and the second one is the brute force method. Okay, so we'll discuss both these methods in the next class. But method number B gives us something which is very interesting. It actually gives us the equation of a circle. Yes, let's not call it brute force method. Yeah, that's a bit unjust. We call it the analysis method. Okay, so we develop the algebraic equations and we try to analyze the behavior of those equations. So method number B actually gives us something very interesting. It gives us the equations of circles. Okay, so we'll discuss it next time, but I'll just show you these circles because they're so popular. You may already have heard of them as the circles called Mohr circles. Okay, so let's draw the circles. Let's understand what they mean, and then we'll stop and catch up in the next class. Okay, so we have three circles here. Let me show you what the axes are. So on the y-axis, we have sigma s, and on the x-axis, we have sigma n. So think about it. I mean, if you have the point P and you have different cutting planes, one of them is this cutting plane which has a normal n hat, it generates your t vector. Now, any cutting plane, any n hat is going to give you um, sigma n comma sigma s. Avinash, can you please switch off your video? It just distracts us. I think he's not hearing us. Anyways, so our state of stress can actually be written as a normal n hat and the corresponding sigma n comma sigma s, because any t vector is nothing but a combination of sigma n and sigma s. Okay, so sigma n and sigma s give us the t vector. So since I can write my state of stress as n hat comma sigma n comma sigma s vector, so I can create a stress plane. That is, I can create a feasible stress region. That is, given any n hat value, you can correspondingly tell me what value sigma n and sigma s takes. Okay, so sigma n comma sigma s gives us one point in this Mohr plane, or the stress plane as we call it. So if you rotate your n hat and you plot all the values of sigma n comma sigma s, you come up with this feasible region. Okay, so there's no way you can go inside the green or the blue circles. There's no way you can go outside the black circle. Okay, so you'll stay in this in this shaded region, which is called the feasible stress region. So what we have here is we have the three principal values. Okay, so if you find the three principal values and you plot them on the x-axis and you create these three circles, what you'll see is that the shaded region will give us the feasible stress region. That is the sigma n comma sigma s points that the stress the stress vector can take. So that's a very interesting idea. It tells us that the sigma n cannot go beyond sigma 1. So that means sigma 1 is the maximum value of normal stress. Similarly, sigma n cannot go below sigma 3. That means sigma 3 is the minimum stress value or the minimum normal stress value in that for a given stress tensor at a given point P. Similarly, my sigma s cannot go. So sigma s max is sigma 1 minus sigma 3 by 2, which is radius of the black circle. Similarly, sigma s min is the negative of that, so it cannot go below that. So these circles are very important, given by the German engineer called Mohr. In the name of him, they are called the Mohr circles. But they're nothing but the analysis of the equations we get in part B, which we'll discuss in the next class in detail. Okay. So we'll stop here, and I'll entertain any questions that you may have. Okay, so if there's no question, then we'll stop this video.